So in the previous session we looked upon again the secant and the tangent slopes, and then we found out that the slope of the tangent is the derivative of the function, and derivative is nothing but it is the way, or it is the behavior, that how the tangent is going to behave, slope of tangent is going to behave for that particular function. If there is a function and there is a derivative of that function, that derivative will tell about that how the tangent is going to behave, or the slope of the tangent is going to behave. Welcome to lecture 3.5. Herein we are going to look to some of the basic rules of differentiation. Differentiation is nothing but the process by which you find the derivative of a function, and we know that derivative is nothing but the slope of the tangent at a given point of time. So we know that when we talk about change, we have got the behavior. Now when we talk about this behavior that is depicted by the function, then came the rate of change. We talked about that change is having behavior as well as it has got the rate of change. Now this rate of change can be two facets. One is the secant or the average rate of change, and the other is the tangent, and nothing but the instantaneous rate of change. We are more focused on the tangent part, as we say that the function, we did the process, we created the derivative, we found the derivative, and thus we got the derivative of a particular function. This whole process is primarily known as differentiation. So let us look to some of the rules of differentiation. Now, what are these rules? What are these rules? The very first rule is known as the derivative of constant. Derivative of constant. Look at scenario. We talked about d by dx of constant. Now if this is a constant value, then this derivative of a constant is always 0. I'll give you an example. Let there be a function which is constant, that is 5. Now derivative of this function which is constant with respect to x. So because this is a constant function, so its derivative would be 0. This is the first rule. The second rule is known as the power rule. Now this power rule states that derivative of a function which is x to the power n with respect to x would always be nx to the power n minus 1. Means herein the n is treated to be a real number. Let us look at example. Say for example x is 3. This is the function. Now this function is in terms of n. The power out here is 3. The d by dx of x cube, this is power of 3, can be directly written as 3, this is the n, 3 out here, x to the power 3 minus 1, and that is nothing but 3x square. The third rule is the constant multiple function. A function having a constant being multiplied. Say for example there is a function, and now this function has got a constant and a function associated to it. So the derivative of this particular function, which is having a constant and a function, would always be equal to, the derivative is taken out, or the constant is taken out, the constant is taken out, and then the derivative of the function is taken. The example related to this is, say for example, the function is equal to 5x square. Now the derivative of this function, d by dx of derivative of this function. Now derivative, as we know, is nothing but the slope of the tangent. We'll take the constant out because this is the constant, and then we'll do the derivation or derivative. We'll find the derivative of this by using the power rule. So it will be equal to 2x, because 2 is going to come over here and x means 2 minus 1. So this is nothing but 10x. The next rule is the sum or difference. Say for example, there are two functions. One is function fx and the other is function gx possibly. Let this be gx. Now it says that the derivative of either the summation of these two functions, maybe function 1 plus or minus function 2 gx, would be nothing but equal to, you can separate them out in such a fashion you can separate them out that you can have the derivative of first function plus or minus whatever it is, the derivative of the second function, that is this. An example could be, now say for example, if it is 2x square plus x plus 3, this is the function. We can have the derivative in such a way that we can separately take the derivative, because this is addition. We can separately have it like this, d of 2x square plus d by dx of x plus d by dx of 3. Now this by the constant rule becomes 0. This is going to be 1, because if I use the power rule, the power becomes 1 and this becomes nothing but 4x. So this becomes 1. So finally it will be summation of 4x plus 1, because this has already been taken as 0. So the derivative of the function which has been given out there because of the sum and difference comes out to be this. So another rule is known as the product rule. Look to a scenario that, say for example, there is a function. We all know that function can be depicted as y. Now this function is the product of two functions, that is u and v. The derivative y prime can be written or can be evaluated or assessed as multiplying the function, the first function u, with the derivative of the second function. Now this is the derivative of the second function plus the second function multiplied by the derivative of first function. An example, just a plain simple example, that let the functions be x and x minus 1. We can evaluate them expanding also. X square minus x can also be done. But let us now look to a situation where this can be treated as u and this can be treated as v. So let us look that f prime of this x based upon the product rule would be this, the first function multiplied by the derivative of the second function. If you take d by dx of v, so dv by dx would be nothing but equal to 1, because if I take derivative of this is a constant, so it is going to be 1 multiplied by 1 plus the next function, that is x minus 1. This is the second function, that is v, multiplied by the derivative of the first function. We also know that the derivative of the first function with respect to x, that is nothing but x, this x will always be equal to 1. So if I evaluate and assess that this is going to be x plus x, x plus x minus 1. So this is going to be equal to 2x minus 1, and this is nothing but the derivative of the function or the product of two functions, that is x into x minus 1. If we take it directly like this, and expanding the function as x square minus x, it will reveal the same kind of derivative. But this we have found using the product rule. Another very important product is, or the rule is known as the quotient rule. Similar to the product rule, if I've got a function which is having the fraction of two functions, that is u and v. Now this is nothing but y. So the y prime or the f prime of x would be equal to v, that is the denominator. Now this v is the denominator function and u is the numerator function. You keep the denominator and multiply it with the derivative of the numerator. Minus, you keep the numerator and multiply it with the derivative of the denominator divided by the square of the denominator. An example can be taken. Maybe let there be a function which states that it is x into x plus 1. So this becomes the numerator or the u, and this becomes the denominator of v. We know that du by dx is going to be 1, as well as dv by dx is going to be again 1. So we find the derivative of this function using the quotient rule. The numerator, that is x plus 1, is taken like that, and the derivative, that is u prime, is going to be 1 minus. Now the numerator as a function, that is x, multiplied by the derivative of the denominator, that is v. This is the derivative of the v. Now this derivative is placed out here, divided by the square of the denominator, that is x plus 1 whole square. If I look to this scenario, then this becomes x plus 1 minus x. So this becomes divided by x plus 1 whole square. So this becomes equals to 1 divided by x square plus 2x plus 1. This is going to be the derivative of the given function. So in the module bygone, we have talked about that how anything which is changing has got a behavior of change and a rate of change. When we talked about the rate of change, we looked into the average rate of change as well as the instantaneous rate of change in terms of derivatives. In the coming lectures, we are going to talk about something which is very exciting, and that is antiderivative.